In this video, I will explain you about p-type semiconductor. So we have seen two divisions for the semiconductors, which are intrinsic semiconductors and extrinsic semiconductor. Intrinsic semiconductor means in that type of semiconductor, we can only see one type of element. See, this is an intrinsic semiconductor. Now, this is a crystal made with only silicon atom. There are no other atom present in it. So, these are intrinsic semiconductor. Now, extrinsic semiconductors means in intrinsic semiconductor, we will replace some of the silicon atom or some of the elements with an impurity. It's not any random impurity, chosen impurity. And which are the choices? These choices are pentavalent impurity or trivalent impurity. Pentavalent impurity means that has got valency of 5 electron, and trivalent impurity means that has got valency of 3. Now, I am going to add a dopant here. Now onwards for the impurity, I am going to call it as dopant. And this dopant is a trivalent dopant. Okay, trivalent impurity I am going to add. Now the process of adding dopant or the process of adding impurity is called as doping. So what I am going to do? I am going to do doping using a trivalent impurity. Can you give me the examples? Aluminium and boron. For adding aluminium, I am going to first remove a silicon. So when I am removing a silicon, this silicon atom has 4 electrons. So this will withdraw its 4 electron from the nearby bonds. Or see, this was contributing 4 electron to share with the nearby silicon atom to form covalent bond. But I have taken a silicon and I am now adding an aluminium here. And aluminium has got 3 valence electron. Now one of the electron it will give for this sheet to form a bond, and one another electron it has will be occupied here to form the bond like before. Now one other electron will be given here. So these are back to the normal position. It has got 3 electron in the valence orbit or outermost orbit. Now this is filled, occupied. All the valence electron of the aluminium are occupied now. It has no more electron in the valence orbit. What is this? This become a hole. This is called as p-type semiconductor. And why we are calling it as p-type semiconductor? Because it has excess hole. Now why I am calling it as excess hole? Is there any free electron present here? Yes. Now at the same time, if it is at a rise temperature means other than 0 Kelvin. 0 Kelvin is not possible. Now if it is at room temperature is 300 Kelvin. So at this temperature there would be lot of electron hole pairs present here. So at room temperature, one of the electron has came out from this position, and this is a electron hole pair, and this is a hole, and this one is an electron. This one is a hole and this one is an electron. See, now in this crystal I can see one electron hole pair, I can see one more electron hole pair, and I can see one more electron hole pair. Now one more hole is present. So this has excess hole, or number of holes compared to number of electrons are more. 4 number of holes and 3 number of free electron. Okay, I have to say these are free electron because these are also electron, but that will not contribute towards conduction. Only these electron will contribute for the conduction. Okay, so here in this case, in p-type semiconductor, number of holes is greater than number of electron, and that is the reason we are calling it as p-type semiconductor. See, number of holes is greater than number of electrons, which means that this has the net charge is positive, but that doesn't mean that the net charge of the crystal is positive. I will explain that why it is not positive. It is net charge of the crystal here is 0. Net charge of the crystal is 0. This is in neutral condition. Okay, but as number of holes is more than number of electron, we are calling it as p-type semiconductor, because see, this means that the total charge of holes is greater than total charge of electron. Okay, as the total charge, when we are comparing the charge carriers, as the total positive charge carriers is greater than total negative charge carriers, we can say that this is positive and these are p-type semiconductor. But I have only taken the perspective of charge carriers here. But if you are taking the total crystal, what would be the net charge of the crystal? See, just go back to the intrinsic nature, that is only silicon atom. Now I am removing a silicon atom from here. Now silicon atom is neutral. Why neutral? Number of protons is equal to number of electrons. I have removed a silicon atom from here, and instead of that I have added an aluminum atom. And aluminum atom was also neutral because number of proton is equal to number of electron. We know in any atom number of protons and number of electrons are equal. Here also it is equal. Now in intrinsic semiconductor net charge is 0. You are very clear, which is made with only silicon atom. Now from there I am taking one silicon which is neutral, and I am adding one aluminum which is also neutral. So from a neutral crystal I have taken a neutral atom and I have added a different neutral atom. So the net charge is 0. So if you have a confusion, then why there is an excess hole here? But if it has got only 3 electrons in the valency, which means the number of protons inside the aluminum nucleus is less. Okay, if it is have 5 electrons in the valency, then that will have more proton in the nucleus to make the net charge neutral. Okay, so the net charge of intrinsic semiconductor and extrinsic semiconductor are neutral. Now go to the definition. Intrinsic semiconductor are added with measured quantity of trivalent element, and mixing of one atom I have added here. So create one hole, see one hole. Net charge of the crystal remains 0. I have explained you. Holes are majority charge carriers and electrons are minority charge carrier. Why? If you are comparing the total number of charge carriers, number of holes is greater than number of electrons. I have explained you that. So these are majority charge carriers and these are minority. Why majority and minority? Just the perspective of numbers. Number of holes are more, number of electrons are less. That's the reason we are calling it as majority charge carrier and minority charge carrier. Now in this case we are controlling the conductivity, because if you are adding more 3 aluminum, so for example in the crystal, then we are giving excess 3 holes. Instead of that, if you are adding 5 aluminum atoms, 5 holes. So we can control the number of charge carriers here. So this makes sense. Okay, extrinsic semiconductors make sense. Now we will see the energy band. So I have told you in this case, let's say this is thermally excited at room temperature. This has got 3 electron hole pairs. So 3 holes it is having, and equal to that it will have electrons. So this is just an extrinsic nature, intrinsic nature. Now when we have added one aluminum, it has got one excess hole. Okay, but these aluminiums is a different atom, right? These silicons are one atom, one type of material, and this one is a different type of material, a different element it is. So this will also be giving a hole, but its energy, energy of these holes would be here. Okay, now I can see, compare number of electrons with number of holes. It has got 4 holes and 3 electrons. So these 3 electrons are thermally generated, and at the same time 3 holes are generated, and this hole is generated by the dopant here. This dopant is also called as acceptors. Why? You know, this holds as a property. Let's say when one electron is moving in this direction, so these holes will attract this electron, so that as it accepts electron, these are called as acceptors. Now we will also learn about donors. Okay, so holes are acceptors, and p-type in p-type semiconductors we are doping acceptors. Acceptors means we are adding trivalent impurity. Okay, now see this energy of acceptors would be slightly greater than the valence band. Okay, this is conduction band, and this one is valence band, and in valence band we have a lot of other electron. So which are these electron? These electron, they are only contributing for the conduction. These are valence electron, and these are its representation in the energy diagram. Okay, now whenever one of the electron get freed, then that electron will jump here and one more hole will be present here. See, for 3 electron in the conduction band, and these are the electron, these are the holes which are made along with the generation of 4 free electron, and this is the excess hole. Okay, thank you.